What I'd like to do today is to cover some of the lunar surface conditions that we had to address for our lunar laser ranging. This work was done mostly in the lunar establishment with Jack Burns as director and funded by the NASA Lunar Science Institute. In the first place, this is not a universal discussion. I will only be addressing those environment conditions which directly affect our Lunar Laser Ranging Retroreflector array for the 21st century, LROD-21, or as we know it in Italy, Moonlight. The LROD-21 issues which affect us may also identify issues that will be of interest to other investigators, and it may identify sources of information that can help others address these issues. The conditions that will be addressed consist of the thermal environment on the lunar surface and the dust environment. The other conditions that one has to address do not strongly affect LROD-21, like launch, deployment. Well, deployment does. Lunar gravity, vacuum, libration affects us, and the magnetic field and electrostatics. In particular, the challenge to our large solid corner reflector that I'll be addressing is the thermal distortion that in turn causes an optical distortion and reduces the signal level. The extreme temperature range on the lunar surface, at the equator, this goes from 370 degrees Kelvin down to about 70 degrees Kelvin. The regolith and or the lander upon which the package is mounted act again as thermal background that radiate more heat to the package. These thermal changes at sunrise or during eclipse produce gradients in temperature, which in turn produce gradients in the cube corner reflector. The index of refraction of fused silica depends upon the temperature, and so these gradients in the temperature cause gradients in the index of refraction, which in turn cause spreading of the beam when it comes back to Earth instead of being focused back on the observatory which sent out the laser. The requirements on this are less than 1 degree Kelvin, actually down around 0.2 degree Kelvin. Otherwise, we get much lower signal level on the Earth. So the areas I'll be addressing are the regolith. We are particularly interested in the surface temperature because that radiates to the package. In addition, there's a depth issue having to do with our anchored deployment and the response during an eclipse. The LSSO mission, which was our initial contract with NASA, addressed a manned mission, and for that we were going to do an anchored deployment, I'll discuss a little bit more later, and we were putting out a blanket, which was a large help, but also complicated the thermal analysis. And then finally, we have the package itself on addressing how we keep the gradients low. These all may sound like problems. They are a little more of a problem than they were in the Apollo, but we do note that the Apollo arrays are still working after 45 years. The only experiment on the Earth, only Apollo experiment on the moon that's still working, and still providing returns of the same accuracy in timing as they originally provided. An illustration of the advantage of getting away from the equator. These are the temperatures at the equator. We're up around 370, 380 degrees, whereas at 65 degrees latitude in the southern hemisphere, we're down around 311, which is small but significant help in the analysis. The first thing we need to address is the behavior of the regolith. The top surface radiates to the package. And so now we must look at, just a second, how this behaves. We've taken the data from the heat flow experiments, particularly in Apollo 17, and used this to define the properties of the regolith. We have here our 1 meter by 1 meter by 3 meters model. And so for a full lunation, and with an eclipse, this is what we do as far as the changes in temperature as a function of depth. In addition to what the soil itself, the lunar regolith, does, for the LSSO mission, as I mentioned, we put out a blanket in the starting thing on this. That's the blue circle, and then the regolith in general is around that. So that if again we go through a lunation, you'll notice that underneath the blanket it's quite uniform. And this was important for the LSSO deployment. In particular, what we did there was we noted that the temperature changes at 1 meter are negligible. And so if we anchored a rod at the 1 meter level with a corner reflector at the surface, then we could get the order of 1/10 of a millimeter stability. However, part of that depends upon the temperature profile seen by the rod supporting the corner reflector. And for that, we needed a careful understanding of what went on at depth. And so this is an enlargement of that same region, where now we see the violet is the blanket itself, and whoops. And here we see that the temperature stability on the rod going down is very uniform. In addition, the package sees the surface of the blanket. And the surface of the blanket has changing temperatures, partly due to simple sun illumination, but more important, due to the illumination shadows that are produced by the package itself. And so what we have over here is what the surface temperatures of the package, of the top of the blanket as the sun rises, goes on top, and then sets. And then at nighttime, it obviously becomes, settles down and becomes uniform. Finally, there's the question of what happens in the corner reflector. Rays coming in at different points on the entrance face have different paths and have different behavior. So we have to put up the order of 1,000 rays spread over the front face. In addition, we have to take care of the fact that the absorption of fused silica depends upon the wavelength. And therefore, we have to split up each of these rays into a couple thousand 1 nanometer bands. And so we track each of these million rays, goes through as it enters one of the small 2 millimeter by 2 meter cells. We compute how much of the ray energy is converted to heat, and the remaining ray energy continues to propagate. It gets to the back face. Some of them are total internally reflected, and so they go back out again, and we have to track that. Others break through and heat the pocket behind the corner reflector. This then gives us a 3-dimensional plus time distribution of the heat loads in the CCR. The program that we require is we first have a analysis of the heat loads in the corner reflector, which I just mentioned. It's on the left. That is then combined with the regolith temperatures from the model that I talked about earlier. These go into a commercial program called Thermal Desktop. This converts the heat loads into temperatures. These temperatures then go into a dedicated IDL program developed at Maryland, which convert the temperatures into the return that one sees on the Earth. Now, concerning the dust. For the Apollo arrays, the nighttime signal level was down by a factor of 10 from what we expected, or is now down by a factor of 10. Various explanations are possible. During lunar day, thermal conditions are extremely stressful, and the signal level goes down by another factor of 10. And so this strongly implies a thermal issue. Note that the magnitude of the signal has gone down, but there's been no degradation in the timing accuracy. So we're not losing any data. We have to have a bigger telescope to get more photons, but the timing is still good on the single photoelectron level. During lunar eclipse, the signal is highly variable. It goes from a very large value down to 0. And what this is implying is that there appears to be dust on the front face of the cube corner reflector, and that the other effects are probably due to the dust on the package itself. And this is a current level, further level of analysis. What is the lunar dust formation mechanism? This can be viewed from the fact that large impacts produce a big area of rock. Then micrometeorites come in and hit those rocks and produce secondary ejecta, little big pieces that are chewed out of the rock. Further impacts both affect the rock and these pieces that were knocked out. And so over time, this is tens of millions of years, we gradually refine those rocks, making them finer and finer, finally producing the kind of regolith that was found by the Apollo astronauts, and samples brought back and temperature measurements made. This means that the formation of this material is a relatively nonlinear process. At the beginning, it grows rather rapidly. As time goes on, it doesn't grow as rapidly. It's mostly a question of making the upper surface finer and finer dust. How do we know this? How do we get information on how much is produced? The dust and regolith are thermally quite different than the rock surface. The specific heats are different, and so therefore, as the temperature changes, one gets different performance. When the regolith builds up on this crater, the rock debris from the crater, the temperatures are indications of whether there's dust on it, how thick the dust is. The Diviner mission observes the surface temperature. These temperatures change during the illumination changes, and this indicates the heat capacity. During sunrise and sunset, we're basically looking at the thicker layers. During lunar eclipse, we can learn about the thinner layers. Observations of craters have been done for tens to hundreds of millions of years. There is a nonlinear aspect of the behavior because of the rapid initial growth. If I take a linear estimate from a crater, the youngest crater, 4 million years, the rate of growth on that crater is within astronomical limits, similar to the rate of growth that we have on dust for the lunar, for the Apollo arrays. Thank you. Any questions? I'd be happy to take. The interest in the moon seems to go up and down. 10 years ago, there was a very high interest. 5 years ago, there was a very low interest. However, these days, it appears that the interest in the U.S. is starting to rise again, somewhat slowly, and the interest in return to the moon by both commercial groups, which is the group I'm working with for carrying it to the moon, and for other countries, ESA, the Russians, China. The interest is high, and it looks like we're going to be able to successfully return to the moon in the next few years. Thank you.